Okay, video number 3, we're going to look specifically at properties of ionic compounds and how those ionic bonds really affect the properties. So to begin with, let's talk about physical structure. So when you have an ionic compound, it is very different than having a molecular compound. In a molecular compound, you have individual molecules. Like for water, you can have one H2O, one molecule of water. Well, with ionic compounds, it doesn't work that way. What you get is a large number of cations and anions, and they're all packed together into a regular repeating pattern that balances out those forces of attraction and repulsion. So you're going to get big geometric structures of a whole bunch of cations and anions all packed together, and that's what gives ionic compounds their crystalline structure. And we call that crystalline structure a crystal lattice. So you can see here we have a bunch of positive and negative cations. They're all nice and neat and stacked together. This actually represents sodium chloride. So those are sodium ions and those are chloride ions, and they're all nice and neat and organized, and that's what gives salt in particular the nice, neat crystalline structure that you see with tiny little grains of salt. Other physical properties, melting point, boiling point, and hardness, they all depend on how strongly the particles are attracted to one another. Now, ionic bonds are relatively strong. Cations and anions attract each other to make a relatively strong bond, which means it requires a large amount of energy to break those ions apart. So ionic compounds have high melting and boiling points. And if you remember way back to the lab that we did comparing properties, the two ionic compounds never melted when you had them on the foil over the Bunsen burner. They didn't get to a high enough temperature to actually melt those solids. Conductivity is dependent upon the movement of charged particles. Since ions are fixed or locked into a fixed position, the solid ionic compounds can't conduct electricity. But when you dissolve an ionic compound in water and the ions are free to move, then the solution is conductive, which is not true of solutions made out of molecular compounds. When you have sugar, which is molecular, dissolved in water, it doesn't conduct electricity the way salt does because there are no ions in a molecular compound like there are in ionic compounds. Ionic crystals are hard, brittle, and rigid solids, which means when an external force is applied, the crystal breaks. If you hit a crystal with a hammer, it's going to shatter because what you can see here is when you hit it, you're actually putting like charges next to each other, and like charges repel, causing that crystal to break apart rather than to bend like other compounds can. Okay, let's write down a definition. Lattice energy is the energy required to separate the ions in an ionic compound. Lattice energy is directly related to the size of the bonded ions and to the charges of the bonded ions. Smaller ions have stronger attractions, therefore they have greater lattice energies. So when you're looking at things at the very top of the periodic table, like maybe sodium and fluorine bonded to each other, those are going to have relatively strong attractions because they're small. All right, now an ionic bond formed from the attraction of ions with larger positive and negative charges also have greater lattice energy. So let's compare potassium fluoride versus potassium iodide. So as you can see, potassium iodide is right here, potassium fluoride is right here, and potassium fluoride has a higher lattice energy because they are both +1 -1 in both compounds, but fluorine is a smaller ion than iodine. If you look at the periodic table, fluorine is up at the top. It is a much smaller ion than the iodide ion, so it's going to be more attracted to the potassium. When we compare sodium fluoride with magnesium oxide, sodium fluoride has a lattice energy of 910. Magnesium oxide down here is, well, almost 4,000 kilojoules per mole. So it is significantly higher where if you look at the sizes, they're about the same. Magnesium and sodium about the same size. Oxygen and fluorine about the same size. So that's not the difference. The difference is sodium has a +1, fluorine has a -1 charge. Magnesium has a +2, oxide has a -2. So that bigger charge is causing a significant increase in the lattice energy. So to have a really high lattice energy, you want small ions with high charges. That's what causes a really strong attraction between the ions.